Good morning, Black Hat. My name is Claudiu Teodorescu, and I'll be presenting the blasting event-driven Cornucopia, representing the binary team. Windows Management Instrumentation provides the ability to manage enterprise devices, both locally and remotely. Various tools, EDRs and SIEM solutions leverage this functionality for performance monitoring and device telemetry gathering. Attacking this functionality can blind all these solutions that rely on this telemetry. And also, this is an important topic for defenders, for experts in Windows security and malware detection and incident response. A little bit about the binary team. So binary is a device security startup based in LA that focuses on threats that originate below the operating system in the firmware and understand how they move up the stack into the operating system and user learn to deploy their next level, their next stages. In 2021 at Black Hat Europe, the same team presented a deep dive on attacks on ETW. For this talk, we chose to attack WMI, and as we'll see through the presentation, we have a lot to talk about. Again, my name is Claudiu Teodorescu. I'm the CTO and co-founder of Binary. Unfortunately, Andrey, Red Plate, and Igor couldn't make the trip to be with us today, but their contribution to this research was essential. So it is very important to understand how we can attack WMI because it is used by a lot of solutions in the field, and these solutions can be blind or it can be tricked in terms of the telemetry that they are gathering. Also, more important is to find ways how to detect if the WMI or any other solution that is used by security solutions is tampered with, and then act upon that by notifying the proper audience. So as for the agenda, we'll start with presenting some information about the Windows Management Information in terms of architecture and features. Also, we'll look at how the hackers and the threat actors are using WMI in the wild. Next, we'll go to the core of the presentation by introducing different types of attack on WMI and also introduce 8 brand new attacks on the WMI. At the end, we'll introduce some solutions that can, some solutions like WMI check and memory ranger. Those solutions can detect and prevent some of the attacks that will be presented in this presentation. Next, let's go a little bit into the Windows Management Instrumentation architecture. For short, WMI actually is the Windows implementation of 2 standards, the WBAM or Web-based Enterprise Management and SIEM Common Information Model. It has very good advantages. It's available system-wide in all the Windows operating systems, starting with Windows NT 4.0. Also, it provides a standardized framework to talk with consumers and providers via COM interfaces. Going into the specifics of the architecture, so we have the WMI providers that produce device telemetry as WMI objects. We have the clients that consume those events. We have the SIEM standard that is structuring, querying, and transmitting the WMI objects. For reference, WMI objects are actually instances of WMI classes. Next, so as part of the SIEM standard, we have the WMI repository that stores the class definitions, the namespace definitions, and their associated properties, as well as the persistent WMI objects. Then we have the MOF, or Managed Object Format. It's a object-oriented language that that is used to specify different WMI artifacts to extend the format. Then we have the query language, that is a SQL-like type language, WQL, to filter events, and to remotely connect and transmit and receive data. Windows Remote Management or DCOM can be leveraged. Last but not the least, we have the WMI service, which is implemented at the SVC host service DLL in the NetSVCS group, which is called WinMGMT. Let's talk a little bit about the WMI providers. So in user mode, they are implemented as COM-based DLLs or as kernel drivers for the kernel component. As you can see in the MOF definition of a provider is an instance of the __ Windows 32 provider standard class. It is identified by a class ID, and as any COM interface, it has its own registry configuration. As we can see in Windows 11, we have more than 4,000 built-in WMI providers that can cover a lot of different device components. Some of them are listed in the table. WMI Advanced. WMI offers a great ability for both attackers and defenders to act on on pretty much every WMI event, which covers mostly any of the operating system events. Also, another great ability offered by WMI is to register permanent event subscriptions. This is very, which obviously will survive a reboot, which is very used in the field by attackers to obtain persistence on those systems. There are two types of events, intrinsic events and extrinsic events. I'll leave the definition to this as reference. Next, we move to filters. It's an instance of __ event filter, WMI class, that specify which events are delivered to the bound consumer. We'll see what bounding means. The most important properties of this class are the event namespace, the query language to filter the events, and also the query itself as expressed as a WQL query. These are the example of the general syntax of a WL query, and also we have two examples, one for intrinsic event query, which actually triggers every time Notepad.exe is launched. And the other one, it's an example of extrinsic event filter, which detects persistence in the run registry key. Next, the consumer. The WMI consumer defines the action to be carried out once a bound event filter has triggered. And in the standard, there are available 5 event consumers to perform actions such as logging, executing scripts or command lines, or even sending notifications. And in terms of, we talked about the permanent event subscription, how is that performed? Is the way persistence and code execution happens in the WMI repository. It's in 3 steps. Create a filter to describe the event to trigger on, create a consumer that describes the action once the filter has triggered, and then bind them using a filter to consumer binding instance to link pretty much the trigger to the action to be performed. So this is a simple example how it can detect when a new service is installed. You create an event filter that monitors for instance creation events at a polling interval for which the target instance is of type Win32 service. Then you create a consumer that will trigger on this when the new service is created and write a notification into the event log using the event viewer consumer. And last but not least, you bind the filter with the consumer to link pretty much the trigger to the action to be performed. Let's talk a little bit about the SIEM repository. It's the database for the WMI that stores the class definitions for the class definition and namespace definitions together with their qualifiers and properties, as well as the persistent objects, WMI objects. Consists of 3 types of files. It's the index BTR, object.data, and mapping 3 mapping files. The index.btr contains the index for the WMI, which is implemented as a B3, organized in index records, stored in pages. The object.data contains the actual class definitions and persistent objects. In the same way, it is organized in records, and those records are stored in pages. And then the mapping has only one purpose: to translate the logical page numbers to their physical page number equivalent for both the object.data and index.btr. As part of the Flare team in FireEye, I reversed the format of WMI and wrote a paper and released several forensic tools with my good friends Willie and Matt. So let's go a little bit deeper into the forensics, how it works in simple terms. So pretty much the search path is constructed by using the identifier of the namespace, class, and the instance. The index.btr is searched, and then the corresponding index record is found, which contains the logical page number in the object data for the record that you are looking for, the record identifier, and its size. Then the mapping file is used to translate the logical page number into its physical equivalent. Then now we have the physical page where the data you are looking for, it's in object.data. You go through that page, record by record, and identify the one that you're looking for by looking at the record ID. Of course, the size in the index record should match the actual size in the objects.data. Also, the same approach can be used for index.btr because it's a B3 implementation, and the pointers to the next nodes in the B3 are specified as logical page numbers. Now that we know how to parse the repository, we did a very quick exercise to figure out what is in actual database for a Lenovo machine. So we saw that in the root WMI namespace we have very interesting classes, starting with Lenovo _ as prefix. One of them is BIOS setting, another one is Lenovo set BIOS setting, another one is Lenovo set BIOS password, and in the right we have the definition, the complete definition with properties in it, for which current setting picked our attention. It's a string, and if we're trying to look in the repository for instances of this class, we have empty results, which means this class is dynamically created on the fly by a custom provider that is implemented by the OEM vendor. So we can use WMI to actually look for non-empty instances of this class, and then printing out the current settings, we have these results. If we magnify a little bit, we see some information about the trusted execution, the TPM, and also about updating the BIOS. Which means that having those classes, you can alter the settings of the BIOS from the user land. Remember that there is a Lenovo _ set BIOS setting. So which means Lenovo provides an interface in the firmware, so the WMI provider can communicate to read or alter the settings, which from my point of view as a device security startup is pretty scary. Also, the standard provides a class, Win32 BIOS, to give us information about the current BIOS version, the device serial number, and also the OEM vendor. So now let's look how WMI is leveraged by both defenders and attackers. For defenders, it's a great tool to use to gather telemetry. For attackers, it's a great living of the land infrastructure to perform malicious activities. So, how the threat actors leverage WMI? Reconnaissance, you can start with reconnaissance, AV detection, and so on. In the next slides, I'll present an example of how in the wild WMI is leveraged for fileless persistence, code execution, and data storage. So pretty much we have a trigger or event filter that triggers several seconds after the system power up to allow the device to boot up, which will this trigger will make the command line event consumer to execute. What it will execute is a PowerShell script that is located in the description property of the option class. So we have the definition of the option class, which has a name and a description, both of them strings. In the description that is called by the consumer, we have the script. If we look at the script, very quick, we see that it extracts the encoded, base64 encoded payload from the name property and decodes it, drops it to disk at the path specified in the configuration, and then it executes the second stage. So the tools that we use in our research, the WM test to showcase the WMI interaction, scripting via VBScript and PowerShell to play with filters and consumers. Also developed our own WMI client to look for running processes. So WMI attacks. Now let's switch to the main topic. The threat model. The threat model of WMI consists of the WMI service that connects and interacts, that communicates with consumers, clients, and providers via advanced LPC ports, LPC channels. Then we have the WMI files, the repository, and the provider DLLs, and so on. We have the configuration and the registry, and also the data in the WMI service memory. And then we split each one in each of the attacks in 5 buckets, depending which are the targets, the WMI data process, the LAPC connections, the files and registries, then the sandboxing of a WMI using a user mode attack, and then sandboxing of WMI using a DCOM attack. So why the WMI attacks are so dangerous? So these attacks have existed in WMI from the beginning, and the reason for that is WMI wasn't built to be used for a security solution. WMI was built just to gather telemetry on the device. Also, the WMI service is not considered a critical app. It doesn't have PPL or a trust label. And the security solutions don't have a way to check if the WMI has been disabled or has been tampered with. So that, on top of that, all these attacks are architectural flaws, which cannot be just fixed with a simple patch. So let's start with the first bucket, which is attacks on files and registry configuration. So you can modify content, you can remove files, you can restrict access to the files on disks, like the files that represent the database or the provider DLLs. In the registry, we have the service configuration and the other WMI internal settings. So the first attack, there is a registry key called enable events. When a new event WMI client comes in, that's the following call stack. An init ESS, which stands for initialized event subsystem, is called. inside the function, the enable events registry value is read. If it's different from 1, then a pointer to the interface is obtained and success is returned. So an attacker basically can write a number different from 1 in the registry value, restart the WMI service, and then everything is disabled. So the WMI infrastructure in the user space, the most important is the service. The main service is is the WMI SVC DLL. It's implemented as a SVC host service DLL. And the other DLLs that are important for our discussion, the WBM core, the rep DRVFS, and WBM MES. So let's look at the template, how this is attacked. So we have the code of a certain DLL, and on the right we have the running memory. So when the DLL is loaded, the global flag is initialized to its default value, in this case 0. In the initialized function, this flag is turned to 1. When a new connection or registration of an event filter comes in, the global flag is checked. If it's true or 1, then the event is processed and success is returned. We have a new connection established and the registration successful. Then an attacker can clear the global flag, so the error path in the dispatch routine is taken, the event is dropped, and then the error is returned. So we'll talk about all these flags. So different flags in different DLLs can be attacked. The only difference is the error returns after the attack when we disable WMI. So we'll start with the global Boolean variable, do not allow new connections. When the WMI core DLL is loaded, then it is set to false. When it is unloaded, in the shutdown method, it is set to true. When a new WMI connection comes in, ensure initialize is finally called. And when it's called, if it's false, then the system is initialized and everything works correctly. If an attacker comes in and turn this value to true, then the initialize will return an error, which is called server stopping. So now it's time for the first demo. Cool. Let's. Thank you. So let's introduce WMI check, which is a tool developed by Andrey Redplate. Consists of a console app and a kernel driver. It can scan the process and parse the WMI internal objects. It can do that for a specific process and also for the whole system. On the right side, we have all the options that are supported. On the left side, it's a screenshot of how WMI check can detect WMI data patching. So you have a snapshot before and after the attack. Comparing the snapshot, you see how the internal flags are modified between different instances. So next demo showing how to detect the previous attack using WMI check. Okay. Next, let's start with the next attack on WMI core event delivery. This is an internal flag, the offset C in the ESE session field of C repository class. Pretty much when the DLL is loaded, the event delivery is set to its default value, which is false. In start event delivery is set to true. In stop event delivery, it is sent to false. Same attack pattern. You have an intrinsic event coming in. You have the deliver intrinsic event function. An attacker will come in and patch this flag to false, so that the WMI as no error is sent. That's actually an error. If you use failed on this error, it returns true. So what happened? All the intrinsic events are disabled. And let's see another demo about how this works. Let's move on. The next attack is a global Boolean variable, which is called shutting down. When the DLL is loaded, it's set to init value, which is false, in the initialize class in C repository. In the initialize method in C repository is sent to false, in the shutdown set to true. This flag is checked in more than 50 functions. So a template of a dispatching routine looks like this. So the obvious attack is just to set the flag to false, because it's reverse logic, and then to true, actually, to make sure that the error is returned. If it's false, then the internal dispatch is executed. Now let's move to another flag in thegglob instance, a global instance at the field at offset 0. Gglob is a global instance for the C globals class. In the constructor we see it is set to 1. In the deinitialize method it is set to 0. And we have this call stack. When a new filter comes in, put object is called, and also calls the get core services next, and then the attack is again obvious. We set this value to 0, so the return is an error, the WMI initialization failure, which will be picked out by the put object, and then return the error. Next, this is the same attack as the previous one. The field at offset 38 in the same gglob instance. The only difference is that the field at offset 38 is actually a pointer to an interface, to WMI core services, and the obvious attack is just setting null or 0 to this value, which will make get core services return the same error as before. Now the word field at offset BC in gglob, it's set to 1 when the DLL is loaded. In uninitialized is set to 0. When a WMI connection comes in, we have the deserialization function file to instance called, and in there we see that if it's 0, it returns error server shutdown in progress, which is an internal error. So the attacker has to set this field to 0. Then the internal error is set, and it's translated to an external error, a WMI error, in the A51 translate error code. And next, it's the G_PESS_M4, which is a global variable that keeps a pointer to an interface. So when the DLL is loaded, it is set to null. Then it is set using the query interface in the init ESS, and then it is released. The interface is, pointer to the interface is released when shutdown ESS is called. So we have this call stack, and we get the last two functions. The exec notification query calls get ESS sync, which is just returning that variable, and then based on the return, if an attacker comes in and patch the global variable and set null to it, then this will the calling function will return the WN not supported. Next, a new type of attack is sandboxing WMI. So WMI service, as we mentioned, communicates with providers and client consumers using advanced LPC connections. Also, it interacts with the file system and the registry, as we mentioned before. So to sandbox WMI service and isolate it from the OS, we have to set the integrity level to untrusted, and we have to revoke the SE impersonate privilege of the service app. And what's happening Then the service becomes isolated. Every connection request will get access denied. And how this is achieved? We can do this in the user land using these two functions, and then you can use DCOM attack in the kernel to modify the token belonging to the WMI service. And as a result, we have a sandboxed WMI service. So let me introduce a memory ranger, which is a solution that can prevent against the DCOM attack on the WMI token of the WMI service process. How this is done? The memory ranger traps the loading of the attacker's driver, creates a separate memory enclave where the attacker's driver is running in, where it doesn't have any access to modify the token belonging to WMI service. So, as a conclusion, we did this research more like to tell the industry that when they're leveraging some type of solutions, they understand the risks that the risks that they are exposed to. So this is, in any case, a bash of that is a very, very interesting and very, very useful solution. Is more like a wake-up call. Be sure you have in place mitigations or way to detect if this functionality has been tampered with, either disabled or to send bogus information. And everything that we showed, all the attacks that we showed are attacking the architectural weaknesses. We call these attacks, most of them are 1-bit change attack. You just flip a bit and everything is disabled. We introduced WMI check that can pretty much detect WMI attacks on the service data, and then memory ranger that can prevent the sandboxing of WMI for the DCOM, the data kernel object, direct kernel object manipulation attack. So another conclusion to conclusion, pretty much, all these attacks can originate from firmware. And right now, firmware is a big blind spot for the industry. And we see every time we have different attacks that originate in firmware that have been stealthy for 6 to 7 years. So I think this is one thing that I want to leave everybody out, that these attacks happen in the user land, but can originate in the firmware. Also want to plug my co-founder and CEO of Binarly talk that follows this talk at 11:10. Which is very interesting one. He will drop 11 new vulnerabilities, and he will talk about exploiting early boot phases. Thank you very much.